Okay, good morning, guys. All right, so hopefully this data looks familiar. This is the data we typed in yesterday with our um, the number of cases in the U.S. of coronavirus since March 1st. So with March 1st being day one, April 7th being day 37. So you see, boom, 1 to 37. There's my data. L3, I stored my residuals in L3 just to make them slightly easier to work with yesterday when I was graphing that residual plot and such. Okay, so got all that going on. And as we expected, when we tried to make a least squared regression line, it did not go well at all for us. And you guys kind of expected this. You knew that the coronavirus in the US has taken a exponential approach. And you've heard a lot in the news about exponential growth and flattening the curve, and with the keyword being curve. So you knew that it wasn't particularly linear. Okay. Um, so my line has kind of failed me. So since my data is curved, let's try to make a model that is also curved. So when I think of curved functions, the first one that comes to mind is x squared. Well, x squared is the red curve. I know x squared is a curve, but it doesn't look very curved in this. And the reason for that is because if I think about my window, in the span of 0 to 40, the coronavirus has gone from 0 to 300 and something thousand, and my graph goes into the 400,000, and x squared just doesn't go up that quickly. So the scale here is making x squared look flat, just because of how big our scale is, and x squared not going up that fast. So let's try, I don't know, x to the fourth. Not bad. It's going up a little quicker. This is a little steeper than the actual data, but that's a heck of a lot better than x squared. I can at least tell it's a curve. We can try x cubed real quick, see what it looks like. Much too slow. So x4, x to the fourth power, was definitely the better option. But now, when I look at the graph, the problem is that it looks like I've got some type of translation to the right, and so to make this fit, I would need to move the graph to the right. So I know to move a function like this to the right, I'm going to try something like, I don't know, x minus 10. That'll move it 10 to the right. Okay, not bad. Actually, a little better than what I was going for. But still, it's an annoyance to try to figure out what power the function is being raised to, and then other transformations and the other constants that are associated with a function like that. So oftentimes it's hard to figure out, and of course it's changing too. Obviously, we're hoping this flattens out and doesn't continue to look like x to the fourth. So what we want to look at is, instead of making our model fit the data, what about making the data fit our model? Which sounds a little sketchy at first, like let's just change the data, make it more linear. But that's not what I mean. So to try to accomplish that, to make the data more linear, so taking the opposite approach, we got to think about, why does data curve? Okay, and when I think about why data curves, there's really two primary reasons that come to mind. Something like we were just looking at, where you've got like an x to the fourth. So we call that the power model, and that is just you've got your variable and it's raised to a power, and maybe there's some other coefficient in there like a. So I've got a coefficient a, he's a constant. I got the power p, he's a constant. Okay, so I can take the variable, raise it to a power. The other way I can make a curved function is with an exponential model, where now the variable is in the exponent. So instead of the variable being raised to a power, now the variable is the power. So I got some constant out front, I got some constant, and it's being raised to the x power. So where a and b are constants. So in either of these cases, all right, when you're dealing with exponents and dealing with how to isolate exponents and such like that, and things like that, what comes to mind is logarithms. right? What comes to mind is logarithms, and that I might be able to take some logs here and separate powers and et cetera, things like that, and make the data look more linear. So that's exactly what we're going to do. And it's going to look the same or very, very similar for both models. And I'm going to use regular logs, but this whole process would also work with natural logs. I'll remind you that again at the end. So I want to get rid of the power so that this looks flatter. It looks more linear. So I'm going to log both sides. So when I log both sides, I end up with log y equals log of a x to the p. Well, log rules tell me that when you've got multiplication in a log, that you can split them up and think about it as two separate logs. And that's what I'm going to do. So rather than thinking about it as log a xp, let's separate it, think about log a and log xp, right? Log rules also tell me that if I have an exponent, that I can bring that down. So we like to call this the disco rule when I taught calculus, is that p can just come down front, no questions asked. You can also go back and forth. So now I have a function that does not have any exponents, and it's going to be flatter. It's going to be more linear. So when I look at this, I had to log my y values and I had to log my x values. But log a is just a constant, and that's going to turn out to be my y-intercept. Well, p is a constant that's attached to x, so he's got to be my slope. So y-intercept is log a, and my slope turns out to be the power. So that's kind of cool that the power ends up being the slope. But I had to log my x values and I had to log my y values to flatten out that data, or to make that data more linear. Very similar process for exponential. Let's log both sides. That's going to give me log y equals log of abx. Again, I can split abx. Boom. Split those guys. Log y, okay. Again, x can come down front via the disco rule. Some of you have asked why there's a disco ball in my room. It's from the disco rule of exponents with logs. So comes down front, and again, a very subtle difference, but kind of an important difference, or at least it's the difference between the two models. So what I see here is log y, so the y values got logged. Log a, still my y-intercept because it's a constant. And then x log b. X here in log b has become my slope, right? Has become my slope. So the biggest difference here, we logged in the power model, we logged both the x values and the y values. Here we logged the y values, but not the x values. The x values did not get logged. So in practical terms, we go back to our data. Let's get rid of both of these lines, all right? And it's exactly what I said. We want to log the x values and we want to log the y values. If we're going to do the power model, and we're going to log the y values, but not the x values for the exponential. And really what it comes down to, guys, is we can identify things about the function or about the graph that might lead me one way or the other. But if all else fails, just check it. It's just try both. And that's exactly what we're going to do. So let's start with let's start with the exponential model, where we just log the y values. So my y values are in L2. So I'm going to take log L2. Boom. L3 has my residuals. I'm going to want my log x values in L4 eventually, like the x first and the y. So I'm actually going to store this in L5 and L5. Okay, so I'm going to log all my y values, store it in L5. Okay, now I'm going to graph, and I'm going to graph my normal x values, and then I'm going to graph my logged y values in L5, and I'm hoping that when I click graph here, that the data is going to look more linear. And in fact, it turned into a snail worm. We have solved coronavirus. Just kidding, our scale's messed up. So we go zoom and zoom stat, and we see it. Definitely better than before. Definitely better than before. Not perfectly linear, but better than before. So I'm going to go to stat. I'm going to go to calculate. Nope. Yes. Although, interesting. Stat calculate. I'm going to go L1 and then L5, and I want to store that equation in right there. All right, and I see my R and my R squared are both higher. We still know that's not perfectly linear, but I'm seeing much higher R values than what you guys uploaded yesterday on your notes, so that's good. There's my A, my slope, and my y-intercept. That equation should be stored in y equals the way I typed it in. So we graph, and we see a not bad line. Not bad line. It's not perfect. And I know it's not perfect because I'm low, and then I'm high for a long time, and then I'm low. But we're doing a heck of a lot better than what we were. Okay? So that was the exponential model. That was logging just the y values. Now let's try logging the x values as well. So I'm going to go to log, and my x values are L1, and I'm going to store residuals are in L3. The log y values are in L5. I'm going to store these guys in L4. Log L1. Boom, store it in L4. Okay. Stat plot. Now, rather than graphing the regular x values, let's graph the logged values. And it appears that we have, what have we done? We have made, oh my goodness, we've made so many people sick. Let's zoom stat. Better when I hadn't touched the data, but still, let's get this line out of here. But still, not as good as my exponential model. Not as good as my exponential model. But then again, I can prove that if I run linreg. This time I'm going to go L4, comma, L5. I don't know why it's not taking me to my normal screen when I run linreg. And we're going to store this in Y1. Boom. Yeah, kind of what I expected. R squared of 90, so better than when I hadn't touched it, but not as good as my exponential model. So exponential would be preferable to power here because it's just making the data more linear, right? And you can see that, again, not perfect, above, below for a long time, above again right there. Okay. All right. So when we talk about transforming data, or when we talk about making models and the data is not linear, we got two options. We can fit our model, we can change our model and make it more curved, but that can be tricky because is it squared, is it cubed, et cetera, and all the different coefficients that go with it. Or we can try to use logs to help us flatten out the data and make a line more appropriate. And there's a lot better examples, guys, than, or I can make, I could have given you made up data where it works out perfectly. And there's a lot of times when it does. This one, our exponential model is pretty dang good. Not perfect, but pretty dang good. But wanted to use some more real world data for you. Okay, so this is something that we're going to build on. But this is the the understanding of today is kind of the foundation for what we'll do next week when just, plugging in to the equation, stuff like that, solving it. So, okay, we transformed it. Now let's find out day 43, what we're predicting, etc. Okay. All right. So if you guys watch that today, we will call that good. And no assignment, just watch this and let me know if you have any questions. All right. Good job, guys. Miss you.